Welcome to Unit 4, Lesson 14. We've been talking about using base E and base 10 and logarithms throughout this entire unit, as well as exponential equations. Lesson 14 and 15 really start talking a lot about solving exponential equations. So we're going to start seeing some equations of different kinds that are asking us to solve them. So 14 is looking at a lot of it as far as equations and using basic algebra and algebraic thinking in order to solve these things. So moving values from one side of the equal sign to the other. Lesson 15 is going to start bringing in the idea of using graphs and tables as well as algebra to solve them. So we're looking at some different strategies we can use to solve equations. And this one we're going to try to focus on the algebraic steps that we would use, the way that we kind of work backwards to undo some values. So we have an equation, 5 times e raised to the 3a power equals 90. And we want to look at what she's doing each step in order to find her answer so we can see if her answer is valid. And then we'll see how we can also check those values to see if we've got it right. So it looks like in her first one, I noticed the difference. She's keeping this e to the 3a the same. And so what she has done is moved this 5 to the other side of the equation. She did the opposite operation. So in each first step here, she divided both sides by 5. These 5s would cancel out. 90 divided by 5 is 18. That makes sense to me how she did that. So I'm feeling good about her answer so far. So I need to think about our next step here. She has a known base e. Remember, that's a number, not a variable. So we know what this base is raised to the 3a power equals 18. It looks like going from step 2 to step 3, she did that good old log roll going on here. So she rolled this e to the other side of the equation, added the log in of base e, and the 3a becomes the exponent. Remember we talked about it's isolating the exponent when you're using a logarithm. So this next step looks good. She used a log to isolate the exponent. There's our step to get from here to there. So now the exponent that is 3a, she's got that isolated, and she's going to take the last step, here it looks like, by dividing both sides by 3. In order to get the unknown part, the a, by itself, because these 3's would cancel out, and she's left with a equals log base e of 18 divided by 3. So yes, her solution is valid. All of her algebraic steps make sense. And if we want to see if she's got it right, remember all of these are numbers. So we could actually type this into our calculator and find what a equals, and we can plug it back in the original to see if we've got it right. So if we really want to make sure what she's got, if we calculate log base e of 18 and divide that answer by 3. I'm going to do this kind of in steps here with my calculator. So I'm going to start with log base e. Now remember, when we're typing this in, one of the ways we can do it is log of the full size number on top divided by log of the base. So I'm going to just do that step first in my calculator. Log 18, close parentheses, divided by log e, close parentheses. And that is looking at about 2.89037178. And we want to take that value and divide it by 3. So here's my answer. Divide that answer by 3, and it equals 0.9634572526, or roughly 0.9635. If this is what I think A equals, I should be able to type it and plug it into the original equation, and maybe we'll see if we get 90 out. So 5 times E raised to the 3, ooh, and I should put that in parentheses, open parentheses, 3 times, and I want to call up that answer because I want to get as close as I can to the original. If you want to call up your answer, it's actually here in the negative button, right above the negative button. Oh, I know that's so blurry. Can't, for some reason, get my camera to focus on my calculator. Maybe it's because it's pink. So if I type in second negative symbol, it's going to pull my most recent answer and it's going to use it in my equation. So I think I'm set to see if this equals 90, and it does, right? So everything that she's done checks out, not only algebraically, but also when we solve out what A equals numerically and plug it back in. I'm just also plugging it in as a decimal, rounded to the 3 places or the 4 places that we had there, and look at how close to 90 it is, even with our rounding. So that's looking really, really good. So when we typed in 5 times E to the 3 times 0.9635, we got 90.011. That's pretty darn good. So I'm calling that valid. Way to go, Lynn. You got it. We're going to use some of those same ideas about opposite operations to isolate unknown values. I'm so glad this is here, this natural logarithm. Natural log is another button on our calculator. It looks like ln, and I love it. Just like when we say something like log 8, and we assume, if there's no number here, that that number is 10. Because we use base E so much, if we have just the ln button of 8, it's gonna assume base E there. Now what's really nice about that is we could have used that idea right here. You see how we wanted log base E of 18? That's the same as natural log ln. They put the L for log first. It's like logarithmic natural, because it's from another country over in Europe. I'm not sure if they decided it in Spain or Greece or Roman times, or wherever they decided to use natural log. They put the adjective first, as so many European countries do. So they have log natural. So here we really could have just typed in ln 18 over 3. Now that ln button, you might be saying, that's something new, that's something different. Look, it's right below the log button. So log uses exponents. Do you notice that? Look at that. Your calculator thought ahead and put opposite operations on a button and a second of that same button. So the opposite of log is 10 to an exponent, and the opposite of natural log is using base E. So if you ever need that reminder of what those values are, if like it's not said in a log, it's right on your calculator above it. So a nice thing to use. So yep, over here we could have just typed in natural log of 18 divided by 3, and check it out, we got that same answer that we got up above. so much easier. So if you have something with base E, you can use natural log and not have to go through that log of the large font number over large log of the base. We can just do the same thing. So here it's got that same thing where we're just kind of rolling that E to the other side. We have ln base E, but they don't have to write it because it's natural log of 1 equals 0. We're just going to practice filling in this table, going from exponential to logarithmic form and back again. All of these are using base E. So instead of log over here, we're going to see ln, or natural log. Remember, our goal is to isolate the exponent, so the exponent should be all by itself in logarithmic form. And here we're going to take ln of E. Rolling that E over to the other side, leaves the exponent all by itself. We're taking a natural log. You're going to see me write it almost in cursive, so you can tell my L's from my 1's, I guess. I'm going to skip down to part E just because I'm doing the same, like kind of focusing on one same operation again and again. And to bring it back, we have a base here. We're kicking it over. That exponent goes up. So we have E to the negative 2 equals 1 over E squared. So natural log works the exact same way as basic log, base 10. We can rewrite them back and forth with no challenges and do an A-OK. When we're looking to solve equations, it asks us to use ln notation, natural log notation, and then find the approximate value using the natural log button on your calculator. So let's rewrite this first. We're going to log roll this guy over. It leaves the exponent by itself. Natural log, because we have base E of 20. And when we go look at that on our calculator, the natural log, ln, right here, of 20 equals 2.99573, or when we round it to 2 decimal places, oh man, 2.996. Natural log, doing the same things as log. Base E is our only difference. Let's see what else we get to do. Oh, looks like we're solving a whole bunch of equations without using a calculator. Just put that off and put it over there for now. Solve each equation. It's expected that some solutions will be expressed using log notation. Remember how we talked in class maybe about how there are rounding times that we can go to 3 decimal places, and there's times we're going to need to keep it in log notation to be exact. So, you know, we're just going to try to get exact if we can, and if we can't, then we're going to stop and just leave it in log form. That's all that that's telling us. All right? So we need to figure out that 10 to some exponent equals 10,000. I feel like we've done this problem a couple times. But let's see, 10 times 10 is 100, times a third 10 is 1,000, times a fourth 10 is 10,000, or by now I'm hoping that you know you just count the zeros. It would be 10 to the fourth, and so x has to equal 4. Number 2, we're doing 5 times 10 to the x. Now remember, please excuse my dear Aunt Sally, or PEMDAS. It's telling us that we need to do the exponent before we do multiplication. So when we're undoing it, we need to do the multiplication and then the exponent. Okay, so remember, we can unwind. This exponent is only applying to the 10, so we can divide both sides by 5 to cancel out that 5 there. 10 to the x equals 100. Well, let's see. How many times do I need to multiply 10 by itself to get to 100? That's telling me it's going to have to be a 2, because 10 times 10 is 100. Alrighty, this one we have the variable in the exponent, and then we're adding 3 to it. So I need to think first that this 10 raised to the x plus 3 equals, how can I write 10,000 as a power of 10? I'm going to go steal my answer right up here. Looks like we wrote it up here as 10 to the 4th. We can do the same thing here, 10 to the 4th power. Now, maybe when we were playing Log War, you remember that if the bases are the same, the exponents also have to be equal. So we need x plus 3 to equal 4. That x has to be 1. There's nothing else it can be. So if we have 1 plus 3, 10 to the 4th power, we would get 10,000. Keep on working through some of this. I'm not going to talk through every single one, but I'm going to keep on thinking about this. We already know 10,000 is 10 to the 4th. So 2 times x has to equal 4. X has to equal 2 on that one. This one I can't get to an exact value without using a calculator. So if I can't get to an exact value, it said we might be expressing it in log notation. So let's just log roll this thing over. Let's leave the x all by itself. That's our goal, is to solve for x. It's base 10, so I don't even have to write anything other than log of 315. The urge right now is to grab my calculator and get that to a decimal, but we have an exact value and we are all set to go. This one, it's tempting to grab the calculator. Oh, it's so tempting. Now that we know, we can just kind of log roll this and type in log 4,000 and then divide that, whatever we get, by the 1.2, but we gotta go in steps here. So I'm going to log roll this. We're left with 1.2x on one side of the equation equals log base 10, so I'm just going to keep it as log of 4,000. Now the log of 4,000 is not an exact value that I can calculate. I would get some kind of a decimal going on there. So if I need to keep this in exact, there's only one more step I can take, and that is to get the x by itself by dividing both sides by 1.2. So that's going to be our final answer here. X equals log 4,000 divided by 1.2. Remember, the exponent only applies to the base, so I can divide both sides by 7. Cancels out the 7. If I need it to equal 10, that has to be to the first power. Now I've got two exponents that have to be equal because these two are in the same base. Same base, equal to each other, same exponent. So 0.5x equals 1 because the exponents have to be equal. I'm going to divide both sides by 0.5. This is where that intuitive thing comes. If I have 1 divided by 0.5, you guys might remember this as copy dot flip-flop. So instead of 1/2, I've got 2 over 1. This equals 2. Should be boxing in all my answers there. So 1 divided by 0.5 is 2. I always think of this if it takes like one Band-Aid to cover half of a wound. If I want to cover the whole wound, I need 2 Band-Aids. Keep plugging and chugging, friends. This time we have a base E. E, remember, is 2.71828182818281828 forever and onwards. So I certainly can't get exact when I'm looking at that as a base to something. All I can do is log roll that to get x by itself. Remember, log base E, natural log ln of 8. And last but not least, number 10. We have an exponent, but we can divide both sides by 10 first. Two 150 divided by 10 is 25. Log roll that E base to the other side. 3x equals the natural log of 25. Last step though, gotta get x by itself. We're not done until x is all by itself. So x equals natural log of 25 divided by 3. Check your answers, make sure you've got them right. There is a little "Are you ready for more?" over here. And we can do those guys too, right? We can always stretch ourselves. 10 to the n equals 16 and 10 to the n equals 2, and to express them as logarithms, just log rolling. N equals log base 10, but I already know base 10 is log without needing to write it. Log 16. So if I'm looking at these two and I'm trying to figure out the relationship between these two solutions and how we know, that's an interesting question. When I start looking at these two values, right, I notice a relationship going on between these two. I have 10 to some power equaling 16 and 10 to some power equaling 2. But these two are also connected to each other. If we look at just the values of them here that we have, the 2 and 16, I can think of this like 2 to the first power. And I can write 16 also in terms of a power of 2. 2 times 2 is 4, times 2 more is 8, times 2 more is 16, so that's 2 to the 4th power. So the fact that we have these two ideas here means that they're going to be somewhat related to each other using these kinds of exponents. And so this one I actually am going to pull in my calculator and see what's going on about the relationship between these two solutions. Because if I look at the log of 16, and if I look at the log of 2, interestingly enough, they're 4 times apart from each other. You see this? How I could take the log of 2, multiply it by 4, and get to the log of 16. And that's because they have the same exponents here, n and n, but we see the exponents here, what they're equaling, their values here. This one's 4 times as much. So if I took this log 2, multiplied it by 4, we would have 4 times that n going on up here as an exponent. It's kind of a stretch, but it's kind of neat to see those kinds of relationships going on and how we can start to see those values. So it all comes from this being 4 times as much in that exponent, the values that we're looking at, that 16 equals 2 to the 4th power, that 2 equals 2 to the 1st power. So this exponent, which we know as n, will be 4 times as much. So, just kind of a neat thing to think about. Alright, so we can solve these algebraically. We did an entire 10 problems without using a calculator at all. That's pretty cool. If you have some extra time, some practice problems where you are solving some more of these things and checking them out. Thanks, friends.